Somewhere out there, the universe is expanding, faster than it should, or slower than it should. Depending on who you ask, physics itself is breaking in real time. Two of the most precise measurements ever made by science stare at the same cosmos and return two different answers. One looks at dying stars exploding in distant galaxies. The other listens to the faint glow left over from the birth of everything. They disagree, and nobody can fix it. If you enjoy unraveling cosmic mysteries, hit subscribe and stay with us. Tonight we follow exploding white dwarfs, listen to gravitational waves from colliding neutron stars, and confront the possibility that our entire model of reality is wrong. Prepare yourselves. We begin. Picture two groups of scientists on opposite sides of the world, both holding what they believe is the correct answer to the same question. Both have spent decades on it. Both have the best instruments ever built. Both are absolutely certain they are right, and their answers do not match. The question sounds simple. How fast is the universe expanding? Every galaxy, every star, every atom is being pulled apart from every other one as space itself stretches like an endless sheet of rubber. There is a number that describes how quickly this stretching happens. Scientists call it the Hubble constant, and finding its true value is one of the most important measurements in all of physics. One team looked outward into the nearby cosmos. They studied exploding stars in galaxies close to our own. They tracked pulsing beacons, measured their brightness, and calculated distances with extreme care. Their answer came back at around 73. That number describes how fast a galaxy moves away from us for every small slice of distance added between us and it. The other team did something completely different. They turned their instruments toward the faint afterglow of the Big Bang itself, a whisper of ancient light still echoing through space from almost 14 billion years ago. They built a model of the infant universe using this light, then calculated what the expansion rate should be today. Their answer came back at around 67, 73 versus 67, a gap of roughly 9%. You might be thinking 9% sounds tiny. A rounding error, a mistake someone will find next Tuesday. But in cosmology, that gap is a canyon. These are the two most carefully checked numbers in modern astronomy. Each team has reduced its uncertainty to razor-thin levels. Each has been independently verified, retested, scrutinized, and confirmed. Neither can find a flaw, and that is exactly what makes it terrifying. When two precise measurements of the same thing refuse to agree, one of three things must be true. Either one team is making a hidden mistake nobody has caught, or both teams are making mistakes, or something much stranger is happening. The universe might be telling us our entire picture of reality has a crack running through it. For years, scientists assumed the gap would close. New instruments, better data, sharper telescopes would resolve the disagreement. The James Webb Space Telescope was expected to finally settle the fight when it launched. Instead, it did the opposite. When Webb pointed its golden mirrors at the same stars used in the local measurement, it confirmed them with even greater accuracy. The local number stayed at 73. The early universe number stayed at 67. The gap did not shrink, it solidified. Imagine measuring a table with two rulers. You expect the same answer. Instead, one ruler says 3 feet, the other says 3 feet 4 inches. Both rulers are perfect. You check them 1,000 times. They keep giving different answers. Either the rulers are lying, or the table is somehow two different lengths at once. That is what the universe is doing right now. And every year that passes, the problem gets worse, not better. The gap has a name. Scientists call it the Hubble tension. And the story of how it began stretches back nearly 100 years to a quiet man staring through a telescope on a California mountain. In 1929, a former lawyer turned astronomer sat at the eyepiece of the largest telescope on Earth. His name was Edwin Hubble, and he was about to kill an idea that had held human imagination for thousands of years. Before Hubble, almost everyone believed the universe was static, unchanging, eternal. The stars hung in their places, the galaxies drifted peacefully, and the cosmos had always looked more or less the way it looked now. Even Albert Einstein, when he first worked out his equations of gravity, added a fudge factor to keep the universe from moving. He called it the cosmological constant. It was his way of forcing nature to behave. Hubble was working at the Mount Wilson Observatory in California, using a telescope with a mirror 100 inches across. At the time, that mirror was a technological marvel, pulling in more light than any instrument humanity had ever built. Night after night, he photographed distant smudges of light called nebulae, little cotton puffs scattered across the sky that no one fully understood. Many astronomers believed these smudges were clouds of gas inside our own Milky Way. Hubble proved they were something far stranger. Each smudge was a separate galaxy, a city of billions of stars, floating at distances so enormous the numbers barely made sense. Our Milky Way was not the whole universe. It was one island among countless others. Then he did something that changed everything. He measured how fast these galaxies were moving. He did this by splitting their light into rainbows and looking at how the colors were stretched. Light from objects moving away from us gets pulled toward the red end of the spectrum, a phenomenon called redshift. The faster something moves away, the more its light reddens. What Hubble saw made his hands shake. Almost every galaxy he looked at was red. Every one of them was moving away from us. And the farther away a galaxy was, the faster it was fleeing. The relationship was clean, clear, and unmistakable. A galaxy twice as far away moved away twice as fast. 3 times as far, 3 times as fast. This meant something impossible. The universe was not static. It was expanding, growing, stretching in every direction at once. Imagine a balloon with dots drawn all over it. Blow the balloon up, and every dot moves away from every other dot. None of them is at the center. None of them is special. Every dot sees all the others running away. That is our universe. Galaxies are the dots. Space itself is the balloon, and something invisible keeps inflating it. When Einstein heard the news, he traveled to California and looked through Hubble's telescope himself. He went back to his equations and removed the cosmological constant he had added. He called it the biggest blunder of his life. The universe had been moving all along, and he had refused to believe it. Hubble's discovery gave birth to modern cosmology. It also raised a haunting question. If the universe is expanding now, then at some point in the past, everything must have been closer together. Rewind the cosmic clock far enough, and all of existence collapses into a single blazing point. The number Hubble wrote down that night, describing how fast this expansion runs, would become one of the most hunted values in science. And almost a century later, that number would split cosmology in two. Here is where the story gets strange in a way most people never truly grasp. When we say the universe is expanding, we do not mean galaxies are flying through space like shrapnel from an explosion. Something far weirder is happening. Space itself is getting bigger. Think about that for a moment. The empty nothing between galaxies, the gap you might assume is just pure vacuum, is actually stretching, growing, becoming more of itself every second. Galaxies are not moving away from each other through space. They are being carried apart by the space between them, inflating. The difference sounds small, but it changes everything. If galaxies were simply flying through a fixed backdrop, there would be a center to the explosion, a point where the blast began. You could travel back to that spot and stand at the birthplace of the universe. But that is not how expansion works. There is no center. Every galaxy sees every other galaxy running away. An observer in a galaxy billions of light years from us would see the exact same thing we see. They would think they were sitting still while the cosmos fled from them in all directions. Picture a loaf of raisin bread rising in an oven. The raisins themselves do not move through the dough. They sit where the baker placed them. But as the dough rises, the space between every raisin grows. A raisin that starts close to another moves apart slowly. A raisin on the opposite side of the loaf moves apart much faster because there is more rising dough between them, more stretching, more growth. Our universe works the same way. The dough is space, the raisins are galaxies, and the rising is relentless. This is where the Hubble constant finally makes sense. It is the rate at which the dough rises. For every unit of distance between two galaxies, space adds a certain amount of new space every second. That number, measured across vast cosmic gulfs, is what scientists have been hunting for almost 100 years. The units are clunky, kilometers per second per megaparsec. Translated into plain English, it means this. For every 3.3 million light-years of distance between us and another galaxy, that galaxy races away from us at a specific speed. The question is, what speed? If the answer is 73, the universe is young, racing, and expanding faster than theory allows. If the answer is 67, the universe is older, calmer, and behaving the way our current models say it should. Now, here is the truly mind-bending part. Far enough away, this stretching adds up. Galaxies at the edge of our observable universe are being carried apart faster than the speed of light. Not because anything is moving that fast through space, but because so much space is being created between them and us that the distance grows faster than light can cross it. This means there are galaxies out there right now whose light will never reach us. Not because they are unreachable, because the universe itself is running away from them faster than light itself can travel. Every second, more galaxies slip past this horizon, vanishing forever. The Hubble constant decides how fast this happens. It decides the fate of everything, and we still cannot agree on what it is. How do you measure the distance to something you can never touch, never reach, never send a probe to? A galaxy so far away its light took millions or billions of years to reach you. You cannot pull out a measuring tape. You cannot bounce a laser off it. You need something cleverer. Astronomers solved this problem by building something called the cosmic distance ladder. Each rung of the ladder uses a different method, and each rung reaches a little farther than the last. You start with things close by, measure them with a method you trust, then use those measurements to calibrate the next method, which reaches farther. Rung by rung, you climb out into the cosmos. The bottom rung is beautifully simple. Hold your finger out in front of your face. Close one eye, then the other. Your finger jumps against the background. That jump happens because your eyes see from slightly different positions. The closer something is, the bigger the jump. Astronomers do the same thing with stars, but on a cosmic scale. They photograph a star once. Then 6 months later, when Earth has traveled to the opposite side of its orbit around the Sun, they photograph it again. The star appears to shift against the distant background, just like your finger did. The size of the shift tells you exactly how far away the star is. This method is called parallax, and it works flawlessly for stars in our own neighborhood. But parallax breaks down after a few thousand light years. Beyond that, the shift becomes too tiny to measure. You need the next rung. That rung uses special stars that pulse with a steady rhythm. Stars whose brightness tells you how far away they are. These stars, which we will meet properly in the next chapter, let astronomers step from our local neighborhood out to nearby galaxies. They extend the ladder by a huge leap. Then comes a third rung. Stars that explode with a specific brightness, detonations so violent they outshine entire galaxies. By comparing how bright these explosions look to how bright they truly are, you can measure distances across most of the observable universe. These are the explosions that let us see the expansion in motion. Each rung depends on the one below it. If your parallax measurements are off by a tiny amount, that error gets carried up the ladder, growing at every step. A small mistake at the bottom becomes a big one near the top, so every rung must be tested and verified with extreme care. Think of it like mapping a mountain range you cannot enter. You can only stand at the edge and use a series of tricks to estimate how far back the peaks go. Each trick works for a certain range. Each trick is calibrated against the last. If any single tool is wrong, the whole map distorts. This ladder is how astronomers arrived at the number 73 for the Hubble constant. They climbed it, step by careful step, all the way out to galaxies hundreds of millions of light years away. They cross-checked each rung, they retested each rung, and they got an answer that refuses to agree with the early universe method. If the ladder is wrong, the error must be hiding in one specific rung. Finding that rung has become an obsession, and one particular type of star sits right in the middle of the ladder, doing most of the heavy lifting. In the outskirts of distant galaxies, certain stars breathe. They swell, they shrink, they glow brighter, then dimmer, then brighter again. On a clockwork rhythm, some pulse every few days. Some take months, and hidden inside that rhythm is a secret that lets us measure the universe. These stars are called Cepheid variables, and without them, we would not know how far away anything beyond our own galaxy is. The discovery came from an astronomer named Henrietta Swan Leavitt in the early 1900s. She worked at Harvard College Observatory, cataloguing thousands of photographic plates taken of the night sky. She was paid less than a cleaning lady and was never allowed to operate a telescope herself. Women were not permitted to do that kind of work at the time. She was given stacks of images and told to measure the brightness of stars. Leavitt noticed something nobody else had caught. Certain pulsing stars in a distant cloud of stars all followed a pattern. The slower they pulsed, the brighter they shone. A star that swelled every 3 days had a specific true brightness. A star that swelled every 30 days had a much greater true brightness. The relationship was precise. It was a mathematical signature hidden in the cosmos. This was a revolution, because if you know how bright a star truly is, and you measure how bright it looks from Earth, you can calculate exactly how far away it must be. A bright candle held at arm's length looks the same as a much brighter floodlight seen from miles away. Both appear equally dim. If you know the true power of the light, you know the distance. Leavitt had found a cosmic measuring stick. Every Cepheid variable in the universe would now whisper its distance to any astronomer patient enough to time its pulse. This is why Edwin Hubble could prove galaxies were distant islands. He spotted Cepheids inside the Andromeda smudge and used Leavitt's rule to calculate how far away it was. The answer put it far outside the Milky Way. The universe suddenly became unimaginably bigger. Today, Cepheids still anchor the distance ladder. The SH0ES team, which gets the local expansion rate of 73, depends heavily on Cepheid measurements. They hunt for these pulsing stars in galaxies that also contain the next rung of the ladder, the exploding white dwarfs we will meet soon. The Cepheids tell them how far away those galaxies are. The explosions let them reach even farther. But Cepheids are tricky. They sit inside dusty galactic environments that can dim their light. They come in slightly different varieties. They can be crowded together with other stars, making them hard to measure cleanly. Critics of the high Hubble value have argued for years that Cepheid measurements might carry a hidden error. Maybe the dust is fooling us. Maybe we are misidentifying some stars. Maybe the pulse rule works differently in different galaxies. Any of these could bend the answer. So astronomers went back and looked again, this time with the most powerful telescope ever built in space. The James Webb Space Telescope can see through dust in ways Hubble never could. When it looked at the same Cepheids, the measurements held. The pulsing lighthouses are not lying, which means the answer is hiding somewhere else. Perhaps in the explosions they help us calibrate. Somewhere in the galactic night, a dead star is stealing. Slowly, silently, it pulls gas from a living companion star, sip by sip, century by century. The dead star has almost no mass of its own worth, speaking of, just a cooling cinder about the size of Earth, but as heavy as the sun. It is called a white dwarf, and once it grows too greedy, it detonates. The explosion that follows outshines an entire galaxy. A single dead star can briefly glow brighter than the 100 billion living stars surrounding it. The event is called a Type 1 supernova, and it is the most precious explosion in all of astronomy. Here is why. Every one of these explosions is almost exactly the same brightness. Most cosmic explosions are chaotic. Big stars die in uneven ways, depending on their size and chemistry. But white dwarfs are different. They can only accumulate mass up to a very specific limit before gravity crushes them into runaway nuclear fusion. That limit is the same everywhere in the universe. So, when a white dwarf finally crosses the line, the blast that follows has the same true brightness every single time, no matter where it happened. This is an astronomer's dream, a standard candle visible across cosmic distances. If every one of these explosions burns with the same power, then measuring how dim one appears from Earth tells you exactly how far away it happened. The dimmer the explosion, the more distant the galaxy. Type 1, a supernovae, can be seen from billions of light years away. They outreach Cepheid stars by a massive margin. This is the rung of the ladder that finally lets astronomers measure galaxies far enough to see the expansion of the universe clearly. In the 1990s, two teams of astronomers used these explosions to do something that shocked the world. They discovered the universe's expansion was not slowing down as everyone expected. It was speeding up. Some invisible force was pushing galaxies apart faster and faster. That force got a name that sounds more like a mystery than a discovery: dark energy. 3 scientists won the Nobel Prize for the finding. But supernovae have to be calibrated. You need to know the true brightness of these explosions before you can trust them as rulers. That is where Cepheid stars come in. Astronomers hunt for galaxies that contain both Cepheids and a recent supernova. The Cepheids tell them how far away the galaxy is. Then they measure how bright the supernova appeared at that known distance. That gives them the true brightness of the explosion. Now they can use supernovae alone to measure far more distant galaxies. This is the chain the SH0ES team uses to arrive at 73. Parallax to Cepheids, Cepheids to supernovae, supernovae to the expansion rate. Critics have poked at this rung too. Maybe not all white dwarfs explode the same way. Maybe there are subtle differences. Maybe the dust between us and the explosion changes what we see. Every concern has been tested. Every objection has been answered. The supernovae, like the Cepheids before them, have held up, and each year the measurement gets sharper, which means the team using these explosions has a rock-solid answer, and that answer still refuses to match what the early universe is telling us. Something has to give. The team is called SH0ES. The name stands for supernova, H0, for the equation of state. H0 is the symbol scientists use for the Hubble constant. The team was put together with one goal: pin down the expansion rate of the local universe with the smallest possible uncertainty. They are led by an astronomer named Adam Rees, who won a Nobel Prize in 2011 for co-discovering dark energy. He knows the value of this measurement better than almost anyone alive. For nearly 2 decades, he and his colleagues have refined their method, hunted for hidden errors, and pushed their precision to razor-thin levels. Their work is exhausting. They do not just pick galaxies at random, they hunt for specific ones. Each target galaxy must contain a recent, Type 1, a supernova, the exploding white dwarf used as a cosmic ruler. It must also contain Cepheid variable stars, the pulsing lighthouses used to calibrate the explosion's true brightness. Finding galaxies with both is rare. Each one is a gold mine. They use the Hubble Space Telescope, named after the same astronomer who started this whole story, to observe these galaxies across hundreds of hours. Each Cepheid must be tracked through multiple pulse cycles to measure its rhythm. Each supernova must be caught during its brightest phase to capture its peak. Every measurement is checked, rechecked, and cross-verified with other methods. The team has done this for 42 galaxies. Some of those galaxies contain several Cepheids. Some contain multiple supernovae. The data set is massive. The statistics are brutal, and the answer keeps coming back the same. The local universe is expanding at roughly 73 kilometers per second per megaparsec. Their latest published result is 73.04, with an uncertainty of about 1%. 1%. That is the stunning part. When Hubble first measured the expansion rate in the 1920s, his answer was off by a factor of 7. For most of the 20th century, astronomers could only agree on the rate within a factor of 2. As recently as the year 2000, the uncertainty was 20%. Now SH0ES has crushed it down to 1%. This is not a sloppy measurement. This is one of the most carefully constructed numbers in all of science. Every time SH0ES releases a new result, they expect the gap with the early universe measurement to shrink. It never does. Each improvement in their technique, each new round of data, locks in 73 more firmly. The number refuses to budge. Critics have thrown every imaginable objection at the result. What about dust hiding inside the host galaxies? SH0ES uses infrared observations that see through dust. What about the metal content of stars affecting the Cepheid pulse relation? SH0ES accounts for that. What about the possibility that white dwarf explosions differ subtly? SH0ES tests that. The team has answered every challenge. Their answer has survived every independent check, and the James Webb Space Telescope, which was supposed to finally expose any hidden mistakes, instead confirmed the SH0ES measurements with even tighter precision. 73 stands. It is real. It is how fast the nearby universe is expanding right now. But somewhere, at the other end of cosmic history, another team has been listening to the universe's very first light, and that light tells a completely different story. Turn on an old television set, the kind with analog antennas, and tune it to a channel that does not exist. The screen fills with a blizzard of static. Most of that noise comes from Earth, but a small fraction of it, a faint whisper hidden in the chaos, comes from the beginning of time itself. This ancient signal is called the cosmic microwave background. It is the oldest light in the universe, and it is raining down on us from every direction in the sky, every second, without stopping. To understand where it came from, rewind the cosmic clock. Play the expansion of the universe in reverse. Galaxies fly together, space shrinks. Everything gets hotter, denser, closer. Keep rewinding past the birth of the first stars, past the first atoms, past the first seconds of existence. You arrive at a universe that is a boiling, blazing fog. In that fog, there were no atoms yet because it was too hot. Atoms require electrons to settle around nuclei, but the early universe was so violently hot that electrons flew freely, zipping through a soup of bare nuclei and photons. Light could not travel through this soup. Every photon smashed into an electron after a ridiculously short distance. The universe glowed white hot, but it was opaque. You could not see through it. Light was trapped everywhere. Then something changed. The universe kept expanding, which means it kept cooling. Roughly 380,000 years after the beginning, the temperature finally dropped low enough for electrons to slow down and stick to nuclei. Atoms formed for the first time. The fog cleared. At that instant, all the photons that had been trapped in the soup suddenly had empty space to travel through. They flew free in every direction. A sudden burst of light released across all of existence simultaneously. That light has been traveling ever since, stretched by 13.8 billion years of cosmic expansion. When it started, that light was the temperature of a star's surface, a blinding white-orange glow. But the stretching of space has pulled its wavelengths longer and longer, shifting it through red, infrared, and deep into the microwave range. Today, that same light has cooled to just a few degrees above absolute zero. It no longer looks like fire. It looks like faint radio static coming from every corner of the sky. This is the cosmic microwave background, the first light, the afterglow of the universe's beginning. Scientists discovered it by accident in 1965, when two radio engineers kept hearing a strange hiss in their antenna. No matter which direction they pointed it, they checked for interference. They cleaned out pigeon droppings. They could not get rid of the signal. It was coming from everywhere at once. They had stumbled onto the echo of creation. Today, satellites like Planck and WMAP have mapped this ancient light with incredible detail. Every ripple, every hotspot, every tiny variation has been measured. And inside those ripples lies a hidden record of what the universe looked like in its infancy. From that record, you can calculate exactly how the universe has evolved since. You can predict, with extraordinary precision, how fast it should be expanding today. That prediction is the other answer. The one that does not agree with the exploding white dwarfs. The one that says the Hubble constant should be 67. In the year 2009, a satellite lifted off from French Guiana with one mission: take the most detailed photograph ever made of the infant universe. Its name was Planck, after the German physicist who helped invent quantum mechanics. Its camera was tuned to see nothing but microwaves, the ancient radio whisper left over from the birth of everything. Planck floated more than 1,000,000 miles from Earth, parked at a stable point in space where it could scan the full sky without interference from our planet's heat or atmosphere. For more than 4 years, it slowly rotated, collecting every faint wiggle in the cosmic background. What it produced looks, at first glance, like a strange oval, speckled with blotches of color. The oval is a map of the entire sky, flattened out. The blotches are temperature differences in the ancient light, tiny ripples where some patches of the infant universe were slightly hotter or slightly colder than their neighbors. The differences are minuscule, about 1 part in 100,000, but hidden inside those ripples is a blueprint of reality. Every blotch is a record of how matter was distributed when the universe was only 380,000 years old. The size and pattern of the blotches depend on the physics of that era. How much ordinary matter existed, how much dark matter, how much dark energy, how curved space was, how fast everything was expanding. Scientists can take this map and feed it into a mathematical model of cosmology. They set the model's parameters until its predictions match what Planck actually saw. When the math locks in, they can run the model forward in time. They can simulate how the universe evolved from that moment to the present day. They can calculate, from first principles, exactly how fast everything should be expanding now. Planck's answer came back at roughly 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. 67, not 73. This measurement is utterly different from what SH0ES does. SH0ES measures the expansion directly by watching nearby galaxies fly apart right now. Planck measures the expansion indirectly by examining the infant universe and calculating what the expansion should be today based on physical laws. Both methods have been pushed to extreme precision. Both methods have been verified. Both teams are confident in their result, and yet they disagree by about 9%. When Planck first released its numbers, many astronomers assumed the local measurement must have an error. The cosmic microwave background seemed harder to fool. It came from the early universe, where physics was simple and well understood. Extracting the Hubble constant from it felt more reliable than climbing a ladder of distance measurements through dusty nearby galaxies. But the gap refused to close. Each new round of data from each side sharpened both numbers without bringing them together. Planck's result has been confirmed by other cosmic microwave background experiments, like the Atacama Cosmology Telescope and the South Pole Telescope, which use completely different instruments on the ground. They all land near 67. Two completely independent methods, two different eras of cosmic history, two rock-solid answers. Both cannot be right. And when a disagreement this size refuses to vanish, it starts meaning something. It starts hinting that our blueprint of reality is missing a piece. 9%. Hold that number in your mind. In everyday life, a 9% difference sounds trivial. If you order a drink and it comes 9% smaller than advertised, you probably do not even notice. If your paycheck arrives 9% lighter, you are annoyed but not alarmed. 9% is the kind of gap humans shrug off all the time. In cosmology, 9% is a catastrophe. Scientists measure the reliability of their results using something called sigma. It sounds technical, but the idea is simple. Sigma tells you how unlikely it is that a disagreement comes from random noise. A 1 sigma gap is common, the kind of difference you see between two honest measurements that happen to wobble slightly. A 2 sigma gap is mildly interesting. A 3 sigma gap raises eyebrows. By the time you reach 5 sigma, physicists declare a discovery. 5 sigma means the chance of the disagreement being a fluke is about 1 in 3.5 million. The gap between the local Hubble constant and the early universe Hubble constant now sits at roughly 5 sigma. In some analyses, it has climbed to 6 or 7 sigma. These are numbers that in any other corner of physics would be ringing alarms. In particle physics, a 5 sigma result is what won the Higgs boson its Nobel Prize. When two measurements disagree by this much, you are not looking at noise. You are looking at reality telling you something is wrong. What could be wrong? There are only 3 honest possibilities. The first is that SH0ES has a hidden mistake somewhere in its distance ladder, some subtle systematic error that has eluded decades of careful checking. Every year, astronomers test this possibility. Every year, the errors they hunt for turn out not to exist. The James Webb Space Telescope pointing at SH0ES targets was meant to be the final test. it confirmed the result. The second possibility is that Planck has a hidden mistake in its interpretation of the cosmic microwave background. Maybe the model used to extract the Hubble constant from the ancient light has a flaw, but here again, other cosmic microwave background experiments using different instruments and different methods all agree with Planck. The 67 number is not a one-team claim. It is a consensus of the early universe. The third possibility is the one that makes cosmologists nervous. Both teams might be right. The universe might actually be expanding at 73 now, while having started with conditions that predict 67. If that is true, something changed between then and now. Something we do not yet understand. Something not included in our current blueprint of reality. That blueprint is called the Standard Model of Cosmology. It is a beautiful framework that has explained almost everything we see in the sky. The cosmic microwave background, the distribution of galaxies, the abundance of elements, the birth and death of stars. For decades, it has passed every test thrown at it. The Hubble tension is the first test it is failing. If the standard model is incomplete, there must be new physics out there. A new particle, a new force, a new form of energy, a new rule of gravity. Something hiding between the cosmic microwave background and the present day, bending the universe's expansion in ways we have not yet mapped. 9% is not a rounding error. 9% is a door that opens onto a different physics than the one we thought we lived in. To understand why cosmologists are losing sleep over this, you have to grasp how interconnected modern physics really is. The standard model of cosmology is not a loose collection of ideas. It is a tightly woven net. Pull on any thread, and the whole net starts to unravel. Every piece of the universe we have ever studied has been plugged into this model. The speed at which galaxies spin, the way light bends around massive objects, the pattern of elements created in the first few minutes of existence, the clustering of galaxies across billions of light years, the temperature of the cosmic microwave background. All of it fits together, all of it works. And within this net, the Hubble constant is not a free parameter you can change without consequences. It is linked to everything else. Change the Hubble constant, and you change the age of the universe. At 67, the universe is about 13.8 billion years old. At 73, it is closer to 13 billion. That sounds like a small difference, but the ages of the oldest stars we have ever observed start to push uncomfortably close to 13 billion years already. A younger universe makes the problem worse. Some ancient stars might end up older than the universe itself, which is obviously impossible. Change the Hubble constant, and you change how much dark energy must exist to explain the expansion we see. Change dark energy, and you change the entire future of the cosmos. The final fate of every galaxy depends on these numbers. Change the Hubble constant, and you change how quickly structure forms in the universe. The rate at which matter clumps into galaxies, clusters, and the vast cosmic web depends on it. If the expansion is faster than we thought, structure should have formed differently than we observe. If the expansion is slower, the same problem appears in reverse. Either way, you break the match between theory and data. This is why scientists cannot just split the difference and pick a number in the middle. 70 is not an acceptable compromise, because that answer does not fit the cosmic microwave background. Neither does 69, nor 71, nor any value in between. The early universe data demands 67. The late universe data demands 73. There is no middle ground. Some cosmologists have compared the situation to a puzzle where you have assembled 90% of the pieces and the picture looks perfect. Then you try to add the final 10% and none of them fit. The pieces you already placed are not wrong. The final pieces are not wrong either. But the puzzle cannot be completed as it currently exists. Something has to be rearranged. Some of the earlier pieces must be in the wrong place. The question is which pieces? If the answer is 67, the problem lies somewhere in how we measure nearby galaxies. Something is distorting the local view. Maybe we live inside an unusual region of space. Maybe the standard candles we trust have subtle flaws that survive every test. If the answer is 73, the problem lies somewhere in the early universe. Something happened in the first few 100,000 years that we have not accounted for. Some unknown energy or particle was present that later faded away. If both are correct, the crisis deepens further. The universe has two different expansion rates in two different eras, and that demands an entire new chapter of physics, a chapter nobody has written yet. This is why cosmologists describe the Hubble tension using words like crisis, tension, anomaly, and fracture. A 9% gap in a system this tightly bound is not small. It is a warning shot. When the James Webb Space Telescope opened its golden eye in space in late 2021, astronomers around the world held their breath. For many, it was not the pictures of baby galaxies or glowing nebulae that they were most eager to see. It was the answer to a single question. Would Webb finally kill the Hubble tension or make it real? The hope was simple. If SH0ES was wrong, if the local expansion rate of 73 was the product of some hidden error in the Hubble Space Telescope's measurements of Cepheid stars, then Webb would catch it. Webb is the most powerful telescope ever sent into space. Its mirror is 6.5 times larger in collecting area than Hubble's. It sees deeper into infrared light, which means it cuts through the dust that clouds distant galaxies. If Cepheids were being dimmed or confused by crowded stellar neighborhoods, Webb should reveal it. Adam Rees and his team pointed Webb at the same Cepheids they had been studying for years. They remeasured distances. They retested the pulse relationship. They scrutinized every assumption that had gone into their number. The result came in early 2023, and then again with more data in the years that followed. Webb confirmed the SH0ES measurements. In some cases, it sharpened them. The Cepheids were not hiding in dust. They were not crowded together with other stars in misleading ways. They were not influenced by some unknown systematic effect. They were exactly as Hubble had seen them. The local Hubble constant did not budge. 73 held. This was a moment of reckoning for cosmology. For years, many scientists had quietly hoped that the tension would vanish as soon as better instruments arrived. Some had bet their careers on this possibility. They believed the gap was an artifact of measurement, not a feature of reality. Webb was supposed to be the verdict, and the verdict was, the measurement is real. The implications were enormous. Ruling out instrument error meant one of the two possibilities left. Either there was still some unknown systematic hiding in the distance ladder, buried beneath all the layers of checks and cross-checks, or the universe itself was doing something the standard model could not explain. Most astronomers took Webb's verdict as a sign that the first possibility was fading. If a telescope that powerful, looking at the same targets with a fundamentally different instrument, could not find a flaw, then a flaw probably was not there, which left new physics on the table. Webb did not stop at Cepheids. It also observed other distance indicators. It looked at red giant stars, which provide an independent rung of the ladder. It observed a type of star called Mira variables, which pulse differently than Cepheids. Each of these alternative methods gives an answer that either lands near 73 or sits slightly lower, but still far enough from 67 to leave the tension intact. This convergence is significant. If the local measurement were flawed, you would expect different methods to disagree with each other. Instead, they all cluster in the high 70s or low 70s. They tell a consistent story. The early universe story tells a different one. Webb had one job when it came to the Hubble tension. Not to solve it, but to confirm it was real. It delivered. Einstein predicted, more than 100 years ago, that gravity bends light. Anything massive enough warps the space around it, and when light passes through that warped region, its path curves. A star passing behind the sun has its light deflected. A galaxy sitting between us and a more distant galaxy acts like a lens, smearing or duplicating the image of whatever is behind it. This effect is called gravitational lensing, and astronomers now use it as a ruler for the cosmos. A ruler that works in a completely different way from Cepheids, supernovae, or the cosmic microwave background. Here is how it works. When a massive galaxy or cluster sits between Earth and some bright distant object, like a quasar, the light from that quasar takes multiple paths around the lensing mass. Each path has a slightly different length. Because light travels at a finite speed, Each image of the quasar arrives at a slightly different time. If the quasar flickers, the flicker shows up in each image at slightly different moments. By measuring these time delays and modeling the shape of the gravitational lens, astronomers can calculate how far away the lens and the quasar must be. And once you have those distances, you have another independent measurement of the Hubble constant. The method is beautiful because it skips the distance ladder entirely. No Cepheids, no supernovae, no calibration chain. It does not depend on the cosmic microwave background either. It is a third, independent approach to the same question. A collaboration called H0 Likau and its successor TD Cosmo has used this technique for years. They have studied several well-known lensing systems, measured time delays, and built detailed models of the lensing galaxies. Their results have landed in the mid to high 70s, right in line with SH0ES, nowhere near Planck. This is striking. A method that has nothing to do with the distance ladder, using completely different physics, arrives at the same answer as the team using exploding white dwarfs. If the local measurement were wrong because of something hidden in Cepheid stars or supernovae, gravitational lensing should not reproduce the error, but it does. The result is not without controversy. Modeling a gravitational lens is hard. You have to make assumptions about how mass is distributed inside the lensing galaxy. Slight differences in those assumptions can change the final Hubble value. Some groups, using more conservative assumptions, have gotten answers closer to Planck. Other groups, using what they argue are more realistic models, stay near 70. This uncertainty means gravitational lensing has not delivered a knockout blow, but it has added weight to the local side of the tension. A third method, independent of the ladder, agrees that the expansion rate looks high. Astronomers are planning to multiply this kind of measurement. Within the next few years, new surveys will discover hundreds of lensed quasars. Each one will become a data point. Each one will whisper its own version of the Hubble constant. As these numbers pile up, the combined result will carry enormous statistical weight. If lensing continues to point at 70 or above, the early universe side will face a very hard choice. Admit that something deep in its model is wrong, or explain why three independent methods all converge on a number their theory forbids. Meanwhile, another alternative method has been quietly building its own case. Not every astronomer trusts Cepheid stars. A small but determined group has spent years arguing that the pulsing lighthouses carry hidden biases. Crowded stellar neighborhoods might distort their light. The precise relationship between pulse period and brightness might drift between galaxies. These critics have pushed hard to replace Cepheids with something simpler. Their answer is red giants. A red giant is what our own sun will become in about 5 billion years. When a star like the sun exhausts the hydrogen in its core, it swells into a bloated, reddish beast, hundreds of times larger than it is now. For a while, it burns a new kind of fuel and glows steadily. Then, at a very specific moment, it reaches the tip of this phase. That moment is called the tip of the red giant branch. At that tip, the star reaches a specific, predictable brightness. This is the key. Just like Cepheids, red giants, at the tip of their evolution, shine at a known brightness. And the tip is the same in every galaxy, regardless of size, age, or chemistry. If you can spot red giants in a galaxy and identify the tip, you have a standard candle. You can calculate distance without ever needing a Cepheid. An astronomer named Wendy Friedman has led this approach for decades. She was part of the original team that first nailed down the Hubble constant to within 10% in the 1990s, and she has been refining distance measurements ever since. Her group uses red giants as their primary rung instead of Cepheids, then calibrates Type 1 a supernovae against those distances. Their answer, over several years of publications, has landed in the range of 69 to 70. That is a crucial number. It is lower than SH0ES, but still noticeably higher than Planck. It sits in a no man's land between the two camps. If Friedman is right, the tension is not as dramatic as SH0ES suggests. 70 is a lot closer to 67 than 73 is. A 3 sigma tension at 70 is uncomfortable but survivable. The standard model might absorb it with small tweaks rather than a full rewrite. This set off a fierce debate. The SH0ES team pushed back, arguing that red giant measurements carry their own systematic problems. Identifying the exact tip of the red giant branch requires careful image analysis, and different techniques can shift the answer by small amounts. The two teams have traded papers for years, each finding small issues in the other's method. When Webb arrived, it looked at red giants too. Some analyses of the new Webb data confirm Friedman's result in the 70s. Other analyses, using different selection criteria, get answers closer to SH0ES. The picture is not fully settled. What red giants have done, whether they end up at 70 or 73, is rule out the possibility that the local measurement is purely a Cepheid problem. Even if you throw out Cepheids entirely and use only red giants, the answer stays well above 67. The tension survives. So now the local side has three independent methods saying something similar: Cepheids at 73, red giants at 70, gravitational lensing in between. Each uses different physics, different stars, different assumptions. They do not all agree perfectly with each other, but none of them land anywhere close to the early universe answer. And yet another method, born from the most violent events in the cosmos, has recently joined the conversation. In August of 2017, deep underground in Louisiana and Washington state, a pair of laser detectors twitched. The twitch was microscopic, smaller than a proton, but the information hidden inside it was enormous. Two neutron stars, each the dense corpse of a dead star crushed into something the size of a city, had spiraled into each other and merged 130 million light-years away. The collision sent ripples through the fabric of space itself. Those ripples were gravitational waves, and they had just arrived on Earth. The detectors are called LIGO, and they were built specifically to catch these waves. Gravitational waves are predicted by Einstein's theory of relativity. They are literal warping of space, squeezing and stretching everything they pass through by amounts so tiny they are almost impossible to detect. LIGO succeeds by using lasers bounced between mirrors in tunnels several miles long. When a wave passes, the tunnels stretch and shrink by a fraction of a proton, and the laser picks up the change. The neutron-star collision was a gift. Unlike black hole mergers, which are invisible to light-based telescopes, neutron-star mergers release enormous amounts of radiation. Within hours of the gravitational wave detection, traditional telescopes around the world found the explosion. The same event had been caught by two completely different kinds of observation. This opened a brand new way to measure the Hubble constant. The method is called standard sirens, to distinguish it from the standard candles of the distance ladder. Here is why it works. When two neutron stars spiral together, the gravitational waves they emit carry encoded information about how violent the collision was. Physicists can calculate, from the shape of the waves, the absolute power of the event. In other words, they know exactly how loud the cosmic siren really is. By comparing that true loudness to how faint the signal arrived, they can calculate the distance to the source. No Cepheids needed, no supernovae, no lensing models, just Einstein's equations and a ripple in space. Then, by measuring the redshift of the galaxy where the merger happened, they can calculate the Hubble constant directly. The answer from that single 2017 event came out at around 70, with a large uncertainty. One detection is not enough to settle anything. The uncertainty was around 15%, but the method is independent. It does not rely on the distance ladder or the cosmic microwave background. It is pure physics-based measurement. Since then, LIGO and its European partner, Virgo, have detected many more mergers. Most have been black hole collisions, which do not emit light and cannot be tied to a specific host galaxy. But a handful of additional neutron star events have been caught. As the catalogue grows, the combined Hubble constant from gravitational waves is slowly tightening. So far, it remains consistent with values in the high 60s or low 70s. The number is not precise enough yet to rule out either side of the tension, but it is getting there. Over the next decade, LIGO and its successors will catch many more mergers. Each one will add a new, independent data point to the Hubble tension. If gravitational wave measurements keep landing above 67, the early universe will be left even more isolated in its claim. The sirens are singing, and each note tells us the same story the distance ladder has been telling all along. Step back and look at the whole landscape. It looks like a war map drawn in numbers. On one side sit all the measurements of the local universe. Cepheid stars calibrating. Type 1 a supernovae give 73. Red giant stars calibrating the same supernovae give 70. Gravitational lensing of quasars gives results in the low to mid-70s. Gravitational waves from colliding neutron stars, with large error bars, land in the 70s too. Different methods, different physics, different assumptions, all arriving, more or less, in the same territory. On the other side sit all the measurements tied to the early universe. Planck's analysis of the cosmic microwave background gives 67.4. The Atacama Cosmology Telescope, using ground-based instruments and a different slice of the sky, gives 67. The South Pole Telescope gives 67. The Baryon Acoustic Oscillation Signal, which is the imprint of ancient sound waves on the distribution of galaxies, also points to early universe values near 67. Different experiments, different skies, different teams, all arriving at the same territory. Every method agrees with itself. Every method disagrees with the other side. This is the strange geometry of the Hubble tension. It is not a case of one rogue measurement sticking out from a cloud of consensus. It is two tight clouds of consensus that do not touch each other. Think about what that means. If the problem were a simple mistake, you would expect to see it in one or two results, not in half the methods in modern cosmology. If the problem were purely random error, you would expect measurements to scatter across a range, not to cluster neatly around two distinct values. The pattern is too clean to be noise. It looks like two answers, not one answer with uncertainty. This is why scientists have been forced to take the tension seriously. Every time a new technique emerges, cosmologists hold their breath, waiting to see which side it lands on. So far, every technique has declared its allegiance to one camp or the other. None have wandered into the middle to suggest the truth might be 70, the halfway point where everyone could compromise. The divide is not random, it is structural. Local measurements, the ones watching galaxies move right now, consistently give a high answer. Early universe measurements, the ones extrapolating from ancient data, consistently give a low answer. The split follows cosmic time. Something between then and now is not being accounted for. That is a powerful clue. It suggests the problem is not with any single method, it is with the bridge between them. The bridge is the standard model of cosmology, which takes early universe data and evolves it forward through 13 billion years of cosmic history. If that bridge has a crack in it, the two ends will not line up. The early universe will predict a universe that expands at 67 today, but the real universe will be expanding at 73. The crack could be anywhere along 13 billion years of history. It could be something that happened in the first few 100,000 years, changing the initial conditions. It could be something that kicked in a few billion years ago, when dark energy started to dominate. It could even be happening right now, in ways we cannot yet detect. Every possibility leads to new physics. Every possibility demands an addition to our current model. The only way to close the gap without new physics is to find a hidden error in enough methods to bring one side to the other, and that is looking less and less possible every year. Dark energy is the biggest mystery in physics that everyone has heard of and almost no one understands. It makes up about 70% of the total content of the universe. It pushes space apart. It is responsible for the accelerating expansion discovered in the late 1990s, and despite 3 decades of research, we still do not know what it is. The standard model assumes dark energy is a constant. It has the same value everywhere in space, and the same value at every moment in time. This assumption is baked into the mathematics that Planck uses to evolve the early universe forward and predict today's Hubble constant. Change the assumption, and the answer changes too. So cosmologists have started asking a dangerous question. What if dark energy is not constant? What if it has changed over time, strengthening or weakening as the universe ages? If dark energy has grown stronger in the last few billion years, the expansion today would be faster than the early universe predicts. That would push the Hubble constant up from 67 to something closer to 73. The tension would vanish. The standard model would just need an upgrade. This idea has teeth. In 2024, a large survey called DESI released its first batch of results on dark energy. DESI, the Dark Energy Spectroscopic Instrument, is mapping the three-dimensional positions of millions of galaxies across billions of light-years of cosmic history. Its goal is to measure how dark energy has behaved over time. The first results were not what anyone expected. DESI found hints that dark energy might actually be weakening slightly, not strengthening. If confirmed, this would not resolve the Hubble tension in the easy way. It would make the situation even more complex, because it would mean dark energy behaves differently than every model predicted. But even the possibility of evolving dark energy is a major shift. For decades, the simplest models treated dark energy as a boring constant, a fixed feature of empty space with no dynamics of its own. A dark energy that changes over time is a very different beast. It would likely be tied to a new field, a new particle, a new mechanism. It would mean the universe contains active, evolving ingredients we have not yet identified. Some theorists have gone further. They propose that dark energy might have a phantom quality, behaving in ways that violate normal energy conditions. Phantom dark energy would speed up the expansion even more aggressively than a constant version, potentially leading to a final catastrophic event called the Big Rip, where expansion becomes so extreme it tears atoms apart. Other theorists suggest dark energy could be oscillating, rising and falling in cycles we have not detected. The appeal of an evolving dark energy explanation is that it keeps the first 380,000 years of cosmic history exactly as Planck sees them. The infant universe stays untouched. The cosmic microwave background is preserved. Only the recent history changes, where dark energy starts to behave in ways we did not anticipate. This is an attractive fix for many cosmologists, because it does not require rewriting the earliest chapters of the universe. But it does require admitting that the 70% of the universe we cannot see is more complicated than we ever imagined. It would mean dark energy is not just a placeholder for what we do not know. It is a living, breathing component of the cosmos with its own biography. If DESI and its follow-up surveys keep finding hints of evolution, the Hubble tension might dissolve into a larger mystery, a mystery about what dark energy actually is, and that mystery would reshape everything. Some cosmologists have looked at the Hubble tension from the opposite end. Instead of tinkering with what dark energy is doing now, they ask a stranger question. What if there was another kind of dark energy in the first moments of the universe? A brief, violent push that lasted only a short time before vanishing without a trace. This idea is called early dark energy, and it has become one of the most discussed possibilities in the field. The concept works like this. Imagine the early universe, still hot and dense, filled with radiation and the first particles forming after the Big Bang. Now imagine that for a narrow window of cosmic history, roughly around the time the cosmic microwave background was emitted, an extra component of energy suddenly appeared. This component behaved a little like dark energy. It pushed space apart slightly more than the standard model predicts. Then, just as quickly, it faded away, decaying into something else or simply dissolving out of importance. A push like this would leave almost no fingerprints on the cosmic microwave background because the extra expansion would happen so briefly. But it would change one critical thing. It would shrink the size of a specific feature in the ancient light, a feature called the sound horizon. The sound horizon is a ruler built into the early universe. When the infant cosmos was still a hot plasma, sound waves rippled through it, creating patterns that froze in place once atoms formed. These patterns are measured in the cosmic microwave background and used to calibrate distances across cosmic history. They are one of the most important inputs into the calculation that gives Planck its answer of 67. If early dark energy shortens this ruler, every distance measurement in the early universe gets recalibrated. The math, rerun with a shorter sound horizon, predicts a higher Hubble constant today. The early universe answer shifts upward, closer to the local answer. In theory, The right amount of early dark energy could close the Hubble tension entirely. 67 could become 73 with one well-placed push. This is why the idea has become so popular. It preserves the standard model almost completely. It leaves dark energy today as a constant. It leaves the rest of cosmic history alone. It only adds one new ingredient in one narrow window of time. But early dark energy has problems of its own. For one thing, nobody has any idea what could actually produce it. Theorists have proposed exotic scalar fields, new particles, or modifications to gravity that switch on briefly in the early universe. None of these have direct evidence. They are constructed specifically to solve the Hubble tension, which makes them feel suspicious. Good physics usually emerges from multiple lines of reasoning, not from a single problem. Another issue is that early dark energy tends to mess up other measurements. When cosmologists run simulations with this ingredient added, they often find that the clustering of galaxies in the later universe no longer matches what we see. The distribution of matter on large scales gets disturbed. Fixing the Hubble tension creates a new tension somewhere else. Still, the idea refuses to die. Every few months, a new theoretical paper explores a different flavor of early dark energy, trying to find a version that solves the Hubble problem without creating new ones. So far, no version has passed every test, but the hunt continues, and while theorists chase early dark energy, other scientists are exploring an even more radical possibility, that the universe contains forces we have never detected. Physics currently recognizes four fundamental forces. Gravity holds planets in orbit and pulls galaxies toward each other. Electromagnetism governs light, chemistry, and the binding of atoms. The strong nuclear force holds the cores of atoms together. The weak nuclear force governs certain kinds of radioactive decay. These four forces explain everything we have ever observed in the laboratory. Every experiment humans have ever run fits within their framework. For a century, the question of whether there might be a fifth force has been asked, tested, and left unanswered. The Hubble tension is reviving this ancient question. If the standard model of cosmology is breaking, the reason might not be a missing particle or a new form of energy. It might be a missing force, something that acts weakly over long distances, something that barely touches ordinary matter but shapes the evolution of space itself, a force so subtle that it has eluded every detector humans have built, but so real that it bends the expansion rate of the universe in ways we cannot ignore. A fifth force of this kind would be strange by design. It would have to be weak enough to have escaped detection in all laboratory experiments. It would have to act on cosmic scales, influencing the motion of galaxies or the stretching of space. It would have to affect the early and late universe differently, producing the kind of shift between Planck's 67 and SH0ES's 73. Theorists have imagined many such forces. Some call them chameleon fields, because they would change their behavior depending on the density of the environment, acting strongly in empty space, but vanishing near massive objects like planets and stars. That would explain why we have never felt them in the lab, yet they could still reshape the universe on the largest scales. Others propose forces tied to dark matter, the invisible substance that outweighs all visible matter by a factor of 5. Dark matter is known to exist because its gravity bends galaxies and galaxy clusters. But we have never detected a dark matter particle directly. Nobody knows what it is made of. Some theories suggest dark matter particles might interact with each other through a hidden force that we have no way to see from the outside. A hidden force among dark matter particles would change how dark matter clumps together. It would change how galaxies form and evolve. It could also change the way the universe expanded through different eras of history. If the force turned on or off at certain times, it could create exactly the kind of shift the Hubble tension demands. This is speculative. There is no direct evidence yet for any fifth force. Every experiment designed to catch one has come up empty. But the Hubble tension keeps planting the seed of doubt. If the two numbers cannot agree, something is adding or removing energy from the cosmic accounting books. A new force is one way to balance them. The search for a fifth force has become more urgent because of the tension. New experiments are being designed specifically to look for subtle extra interactions between particles. Satellites are being proposed to test gravity over long distances. Every new telescope that comes online is tasked, among other goals, with hunting for deviations that might point toward a hidden force. If such a force exists, finding it would change physics forever. It would not just resolve the Hubble tension. It would open a door to an entire new sector of reality, full of particles and fields we never knew were there. And some theorists think gravity itself might be the culprit. Albert Einstein's theory of general relativity has been tested for more than 100 years. It has passed every test. It has predicted the bending of light around the sun. It has predicted the slowing of clocks in strong gravitational fields. It has predicted gravitational waves. Every time scientists have pointed an experiment at general relativity, it has come back with flying colors. So, when cosmologists started whispering that the Hubble tension might require rewriting gravity, many physicists rolled their eyes. Gravity is the most trusted theory in physics. You do not mess with it lightly. But the numbers keep not adding up, and some theorists have started asking whether general relativity, beautiful as it is, might be incomplete on the largest scales. The idea is subtle. General relativity works perfectly within the solar system. It works in binary star systems. It works around black holes. It has been confirmed in every environment we can test directly. But the universe as a whole is a much bigger beast. The cosmic web of galaxies stretches across billions of light years. It is possible that on those scales, gravity behaves differently than our equations predict. One class of theories is called modified gravity. Instead of adding new particles or new forms of energy, modified gravity proposes that the law of gravity itself needs a small correction. That correction would be invisible in the solar system, but would become important on cosmic scales. It would change how space expands, how galaxies cluster, and how light bends across vast distances. A particularly popular version is called MOND, short for Modified Newtonian Dynamics. MOND was originally proposed to explain why galaxies rotate faster than their visible mass should allow. Instead of invoking dark matter, MOND suggests that at very low accelerations, gravity behaves differently from Newton's and Einstein's predictions. MOND has had mixed success. It does well for individual galaxies but struggles with larger structures like galaxy clusters. Extensions of MOND and related theories have been applied to the Hubble tension. Some find that modified gravity can shift the expansion rate by just the right amount. Others find that modifying gravity creates its own set of problems, breaking other observations. The tricky thing about modified gravity is that general relativity has passed so many tests that any modification has to thread a very narrow needle. It has to vanish in the solar system. It has to barely affect the cosmic microwave background. It has to produce a modest change in the expansion rate in recent cosmic history. It has to not mess up gravitational lensing or the clustering of galaxies. Most proposed modifications fail at least one of these requirements, but some survive. And as the Hubble tension refuses to go away, theorists keep exploring new variations. Some involve extra dimensions of space, invisible to us but affecting gravity on cosmic scales. Others involve couplings between gravity and dark matter or dark energy. A few suggest that the fabric of space itself has hidden structure, with gravity flowing through it differently than we imagine. None of these theories has strong evidence. Most remain mathematical playgrounds for theorists. But the Hubble tension has given them more attention than they have received in decades. When the standard framework cannot explain what telescopes are seeing, the wildest ideas start to look more reasonable. If gravity itself needs rewriting, the consequences would ripple through all of physics. Our understanding of black holes, the Big Bang, and the fate of the cosmos would all need revision. A small correction to Einstein's equations could become the biggest shift in physics since Einstein himself. And the possibilities keep getting stranger. What if the tension is not a cosmic problem at all, but a local one? Here is a possibility that sounds almost paranoid. What if there is nothing wrong with cosmology and nothing wrong with our measurements? What if the universe is expanding at 67, exactly as Planck says, but we just happen to live in a peculiar spot that makes it look like 73? This idea is called the void hypothesis. It suggests that Earth, along with the Milky Way and the galaxies around us, sits inside a giant region of space where matter is less dense than average. a cosmic hole, a bubble of relative emptiness inside the larger fabric of the universe. If we live inside such a void, the galaxies around us would be pulled outward toward the denser regions surrounding our bubble. That outward pull would add to the normal expansion of the universe, making our local patch of space appear to expand faster than the cosmic average. When SH0ES measures galaxies within a few 100 million light-years of Earth, they might be catching this extra motion on top of the true expansion. The void hypothesis has a strange elegance. It does not require new physics. It does not require evolving dark energy or hidden forces. It only requires that we happen to be located in a slightly underdense region of space. The true Hubble constant would still be 67, exactly as Planck sees. Our local measurements would be contaminated by our position, not by bad methodology. Astronomers have actually found evidence of large-scale underdensities near our location. Galaxy surveys have mapped the density of matter out to billions of light-years, and there are hints that our corner of the universe might be slightly less crowded than average. Some researchers have argued that a void extending about 600 million light-years from Earth could account for a significant chunk of the Hubble tension, but not all the way. Detailed analyses suggest that even a generous void would only explain part of the 9% gap. It would bring SH0ES closer to Planck, but not close enough. Something else would still be needed. There are also philosophical objections. The standard cosmological principle assumes that the universe looks roughly the same everywhere, on large scales. This is a foundational belief in modern cosmology. If we happen to live in a special region that distorts our view, it violates the principle. Earth would be, in some sense, a cosmically unusual place. That feels uncomfortable. History has repeatedly taught us that we are not special. Earth is not the center of the solar system. The Sun is not the center of the Milky Way. The Milky Way is not the center of anything. To now say we live inside a rare, underdense bubble would reverse this pattern. Still, the void hypothesis cannot be ruled out. Some recent surveys have tried to measure the density of our local region more precisely. Results are mixed. Some find a void, others find nothing unusual. The picture remains blurry. A definitive test may come from the next generation of galaxy surveys. Missions like Euclid and the Vera Rubin Observatory will map the large-scale structure of the universe with unprecedented detail. They will pin down whether we live in an ordinary region or a special one. If they find a dramatic void, the Hubble tension might ease without new physics. If they find no void, the mystery deepens. The universe might be perfectly well behaved. We might just be standing in the wrong spot to see it clearly. Or perhaps the problem runs deeper than location. Perhaps gravity itself is lying to us. Einstein gave us a theory so beautiful that generations of physicists have been reluctant to touch it. General relativity describes gravity as the curvature of space and time caused by mass and energy. Heavy objects warp the fabric of the cosmos, and other objects follow the warps. It is a picture of stunning mathematical elegance, and it has survived every experimental challenge. But surviving every challenge is not the same as being complete. We know general relativity is not the final word on gravity. It breaks down at the center of black holes, where the equations produce infinities that physicists call singularities. It breaks down at the first instant of the Big Bang, where the same infinities reappear. It does not mesh smoothly with quantum mechanics, the theory that governs the tiny world of particles. Somewhere, somehow, Einstein's theory must be part of a larger framework we have not yet discovered. The Hubble tension is prompting scientists to ask whether that larger framework is starting to show its edges, even on cosmic scales. Modified gravity theories come in many flavors. One family, called scalar tensor theories, adds a new field to the equations of gravity. This field can act a bit like dark energy, but with extra flexibility. It can change strength over time, making the universe expand at different rates in different eras. With careful tuning, such theories can shift the predicted Hubble constant without breaking other observations. Another family, called F of R theories, modifies the basic mathematical structure of general relativity. Einstein's equations include a term called the Ricci scalar, which describes how space curves. F of R theories replace that single term with a more complicated function, allowing gravity to behave slightly differently in different regions or at different scales. These theories are mathematically rich but difficult to test directly. A wilder family invokes extra dimensions of space. Some versions of string theory and related ideas suggest that our familiar three-dimensional space is actually embedded in a higher dimensional structure. Gravity might leak into these extra dimensions, weakening or strengthening depending on scale. Such leakage could, in principle, change the expansion rate in ways that mimic the Hubble tension. Every modified gravity theory faces the same challenge. It has to reproduce all the successes of general relativity in the places where we have tested it. The motion of Mercury around the Sun, the bending of starlight near massive objects, the precession of binary pulsars, gravitational waves, the behavior of light in the cosmic microwave background. A single failure kills the theory. So far, no modified gravity theory has emerged as a clean winner. Some shift the Hubble constant in the right direction, but produce other problems, like changes to the large-scale clustering of galaxies. Others keep the large-scale structure correct but fail to produce enough shift in the expansion rate. Theorists are caught in a game of whack-a-mole, patching one issue and creating another. Nevertheless, the search continues. Every year, new ideas emerge. Every year, new data comes in from telescopes and satellites to test them. Most ideas will fail, but one of them, or some combination of them, might eventually survive. If modified gravity turns out to be the answer, Einstein will still be right about almost everything. His theory will remain a stunning approximation, but his equations will need a subtle correction, a new term that only matters on the larger scales. That correction might tell us something profound about the deep structure of reality. And while theorists argue about gravity, other scientists are looking for more exotic culprits. Ghost particles hiding in the data. Deep in the standard model of particle physics, there is a ghost, a particle that almost does not exist. It barely interacts with anything. Billions of them pass through your body every second without a single collision. They slip through Earth as if the planet were made of empty space. They are called neutrinos, and they are real. 3 known types have been detected in laboratories. A fourth, if it exists, would be even more ghostly. The possibility of a fourth neutrino, called a sterile neutrino, has haunted physics for decades. Sterile neutrinos would not even interact through the weak force the way normal neutrinos do. They would interact only through gravity. That would make them almost impossible to detect directly, but it would also make them a natural candidate for dark matter and a natural candidate for messing with cosmology. If sterile neutrinos existed in the early universe, they would add an extra component to the energy budget. That extra energy would change how the infant cosmos expanded. It would change the size of the sound horizon, the ruler used to calibrate Planck's measurement. A different ruler means a different Hubble constant calculation. The predicted answer could shift from 67 towards 73. This is why sterile neutrinos have become one of the candidates scientists watch for when looking for solutions to the Hubble tension. Their addition to the cosmic soup would be invisible in normal experiments, but would leave subtle signatures in the cosmic microwave background. Analyses have tried to fit the Planck data with sterile neutrinos included. Some find that a small addition helps ease the tension. Others find that too much sterile neutrino disrupts other observations. The evidence for sterile neutrinos in laboratory experiments has been contested for years. A series of anomalies in reactor experiments hinted at their existence, but follow-up studies mostly ruled them out. The most recent large-scale searches have not found them, but the question remains open. Other ghost particles have been proposed as well. Axions are hypothetical particles originally suggested to solve an unrelated problem in particle physics. They would be extraordinarily light and would weakly interact with ordinary matter. If they exist, they could make up some or all of dark matter, and their presence in the early universe could alter cosmic expansion. Then there are entire hypothetical sectors of physics, called hidden sectors or dark sectors, populated by particles that interact mainly with themselves. A dark sector could have its own forces, its own dynamics, its own history. It could have influenced the early universe in ways we cannot see directly, but which would leave traces in the cosmic expansion rate. These ghost particle explanations share a common theme. They all propose that the universe contains more ingredients than we currently track. The standard model, both of cosmology and of particle physics, might be missing entire categories of matter or energy. If so, the Hubble tension would be a symptom of a deeper incompleteness. Experiments are searching for these particles. Underground detectors sit in old mines, waiting for the faint touch of a dark matter particle. Specialized telescopes look for the subtle imprints of new particles on cosmic radiation. The Large Hadron Collider probes ever higher energies, hoping to produce exotic particles in controlled collisions. So far, no confirmed detection has come back. The hunt continues because the clues keep accumulating. The Hubble tension is one, galactic rotation curves are another. The distribution of matter in galaxy clusters is a third. Something invisible is out there, pulling strings behind the scenes. And if that something is strange enough, it might force us to consider possibilities that stretch the imagination to its breaking point. There is an idea that floats at the edge of serious physics, uncomfortable to many scientists but impossible to dismiss. The idea is that our universe might be one of many, a vast cosmic ensemble of separate universes, each with its own laws, its own constants, its own history. The multiverse is not a single theory. It is a cluster of related ideas that emerge from different branches of physics. Some versions come from inflation theory, which suggests that the rapid expansion at the beginning of our universe might still be happening in other regions, constantly spawning new universes like bubbles in a foam. Other versions come from string theory, which predicts an enormous number of possible configurations of physical law, each corresponding to a different universe. Still others come from quantum mechanics itself, where the many worlds interpretation imagines that every quantum event splits reality into separate branches. Most physicists are wary of the multiverse because it is hard to test. If other universes are completely separated from ours, we cannot observe them, we cannot compare, we cannot run experiments on them. A hypothesis that cannot be tested sits uncomfortably outside the normal methods of science. But the Hubble tension has given multiverse thinkers an opening. If our universe has unusual properties, maybe that is because we are simply in a universe where those properties happen to hold. The fine-tuning of physical constants, the specific laws we observe, even the mysteries of dark matter and dark energy could all be explained by a kind of cosmic lottery. We won one particular ticket. Other universes have different tickets. In this framework, the Hubble constant might not even be a fixed quantity across all of reality. It might be just one of countless possible values, determined by the specific conditions of our universe's birth. The tension we see might reflect some subtle property of our cosmos that we do not yet understand, a property that would be different in a neighboring universe. Some cosmologists have even considered the possibility that the early and late universe expansion rates genuinely differ because our cosmic neighborhood has distinctive features. The multiverse would provide a backdrop in which such features would not be surprising. They would simply be our universe's version of reality. This is deeply unsatisfying to many scientists. The multiverse feels like a cop-out, a way to explain any observation by saying we happen to live in a universe where that observation holds. It does not predict anything new. It just accommodates what we already see. But others argue that the multiverse might be an unavoidable consequence of modern physics. If inflation is correct, the mechanism that drove the early universe's rapid expansion probably creates multiple regions with different properties. If string theory is correct, there are many possible configurations of physical law, and the equations suggest that all of them might be realized somewhere. The multiverse does not solve the Hubble tension in a satisfying way. It offers no specific prediction, no testable number, no mechanism we can search for in experiments. It simply provides a context in which the tension might not be a problem at all, just a feature of our particular universe. Most scientists treat the multiverse as a last resort. If every other explanation fails, and the tension refuses to yield to new physics of the normal kind, then perhaps we will be forced to accept that the universe we inhabit is one of many. Until then, the search for concrete answers continues, and one of those concrete answers might involve a possibility that is even harder to swallow. that the laws of physics themselves have changed. One of the bedrock assumptions of science is that the laws of physics are the same everywhere and at all times. A hydrogen atom in the early universe behaves the same as a hydrogen atom today. The speed of light is a constant. The strength of gravity never wavers. The fundamental rules never shift. This assumption has allowed astronomers to study the distant past by studying distant light. When we look at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. We apply the same physics to understand what we see, confident that the physics is universal. If the laws were changing, every interpretation of cosmic observations would be in question. The Hubble tension has revived an old, uncomfortable question. What if the laws are not perfectly stable? What if some fundamental constants have drifted over the history of the universe? The idea is not as wild as it first sounds. Some theories that attempt to unify physics, including certain versions of string theory, naturally predict that constants like the strength of gravity or the masses of particles might depend on the environment. In the early universe, those constants might have had slightly different values. Over time, as the universe evolved, they might have settled into the values we measure today. If any of this is true, cosmic measurements from different eras might not match up. The early universe, governed by slightly different constants, would produce a different expansion history. The late universe, governed by today's constants, would produce a different one. The mismatch could look exactly like the Hubble tension. Physicists have actually searched for evidence of drifting constants. One of the most studied is the fine structure constant, which sets the strength of electromagnetic interactions. It appears in the colors of light emitted by atoms. By looking at the light from very distant quasars, which pass through clouds of ancient gas on its way to Earth, astronomers can check whether the fine structure constant was the same billions of years ago. So far, the results have been ambiguous. Some analyses hint at tiny variations. Others find no change within measurement precision. Similar searches have been done for the gravitational constant, the ratio of particle masses, and other fundamental numbers. Most have come back consistent with constant values. But the uncertainties are large enough that small drifts could not be ruled out. If physics has been changing across cosmic time, even in small ways, the implications would be enormous. Every distance measurement we make of ancient galaxies would need to be reconsidered. Every prediction about the early universe would need to account for different underlying physics. The Hubble tension might be just the tip of a much larger puzzle. But most cosmologists consider this possibility unlikely. The assumption of constant physics is not just a philosophical convenience. It is supported by many observations, from the stability of atomic spectra in distant galaxies to the behavior of cosmic microwave background radiation. If the laws were changing significantly, we would expect to see many more anomalies than just the Hubble tension. Still, the possibility remains open, and it points toward one of the most unsettling conclusions the Hubble tension could force on us: that our entire model of reality might need to be thrown out and built again from scratch. Most scientists working on the Hubble tension are looking for a tweak, a small adjustment, an extra ingredient that, when added to the standard model, closes the gap and preserves everything we have built. The hope is that cosmology will survive the tension with only modest revisions. But a growing minority of researchers are whispering a more unsettling possibility. What if the standard model of cosmology is not just incomplete, but wrong at a much deeper level? What if the entire framework we have used for decades to understand the universe is built on shaky ground? This is a hard thing to say out loud. The standard model of cosmology has been stunningly successful. It has predicted the cosmic microwave background, explained the abundance of chemical elements created after the Big Bang, described the growth of galaxies over billions of years, and made quantitative sense of thousands of different measurements. It has the structure of a theory that should be correct, and yet the tension does not go away. It deepens. If the standard model is fundamentally wrong, the path forward becomes unclear. Which pieces do we keep? Which do we throw away? How do we know what to replace them with? Scientific revolutions of this scale have happened before. Newton's physics gave way to Einstein's. Classical physics gave way to quantum mechanics. Each time, a beautiful and successful framework turned out to be a limiting case of something larger and stranger. Cosmology might be heading for such a revolution. The clues are accumulating. The Hubble tension is the most dramatic, but it is not the only one. A similar tension exists in measurements of how matter clusters in the universe, called the sigma-8 tension. Different methods give different answers. The gap is smaller than the Hubble tension but still persistent. Other anomalies appear in galaxy surveys, in the behavior of certain ancient galaxies that seem to have formed too early, in subtle features of the cosmic microwave background that do not quite fit the standard model. No single one of these is damning. Together, they suggest a pattern. Some cosmologists have argued that our standard model might be a sophisticated approximation that works well in certain regimes but fails in others. Like Newtonian gravity, which describes planetary motion beautifully but cannot handle extreme situations like black holes. The framework might be useful without being fundamentally true. If this is the case, the real theory of cosmology is still waiting to be discovered. It would have to reduce to the standard model in the regimes where the standard model works. It would have to explain the Hubble tension, the sigma-8 tension, and all the other anomalies. It would have to be testable, making new predictions that future telescopes can check. Nobody knows what such a theory looks like. Theorists are exploring many directions, but none has emerged as a clear candidate. The field is stuck in a strange place, knowing something might be wrong but unable to see the right path forward. This is uncomfortable. Science thrives on progress. When progress stalls, scientists start questioning their assumptions, and that questioning is painful. Careers have been built on the standard model. Textbooks are written around it. Entire research programs depend on it. Admitting it might be fundamentally wrong would shake the foundations of the field. But science eventually goes where the evidence leads. And the evidence, right now, is whispering that our picture of the cosmos is missing something essential. Whatever that missing piece is, it will reshape not just our understanding of expansion, but of time itself. The age of the universe is one of those numbers that shows up in every science textbook, 13.8 billion years. It is printed on posters, cited in documentaries, and memorized by school children. It feels solid, settled, indisputable. It is not. The age of the universe is not measured directly. Nobody has a cosmic odometer. The number comes from combining several other measurements, including the Hubble constant. When you plug 67 into the equations, you get an age of about 13.8 billion years. When you plug 73 into the same equations, you get an age closer to 13 billion years, a gap of 800 million years. That is roughly how long complex animals have existed on Earth, an enormous difference by any measure. This age discrepancy creates its own problems. Astronomers have spent decades identifying extremely old stars, objects that formed when the universe was still young. The oldest stars in our galaxy have been carefully dated using their chemistry and brightness. The best estimates place them at around 13 billion years old, give or take. Here is the catch. If the universe is truly 13 billion years old, those ancient stars would have had to form almost immediately after the Big Bang. Their formation would have had to happen faster than current models of galaxy formation allow. Some of them might even need to be older than the universe itself, which is obviously impossible. A universe of 13.8 billion years leaves comfortable breathing room. There is time for the first generation of stars to form and die, seeding the cosmos with the heavy elements needed for later stars. There is time for structure to build up gradually. Everything fits. A universe of 13 billion years starts to feel cramped. The timeline becomes tight. The oldest stars become suspicious. The early galaxies detected by the James Webb Space Telescope, some of which appear to have formed far faster than expected, become even more puzzling. This is yet another way in which the Hubble tension is not just a number on a chart. It has consequences that ripple through every corner of astronomy. It changes our understanding of when the first stars lit up. It changes our understanding of how quickly galaxies assembled. It changes the timeline of cosmic evolution itself. Some cosmologists have argued that the tension between star ages and the local Hubble constant is one more reason to trust the Planck value. If the universe really is younger than 67 predicts, we run out of time. The lower age simply does not accommodate the oldest objects we see. But that argument cuts both ways. If the local measurements are correct, it means our models of early star and galaxy formation must be wrong. Either the universe is older than 73 implies, or stars and galaxies formed much more rapidly than we thought. And then there is the Webb telescope, which has complicated everything by discovering massive galaxies that existed just a few 100 million years after the Big Bang. These galaxies look more mature than any theory predicted. They formed too fast. They grew too big. They seem, to some astronomers, almost impossible. Taken together, the evidence suggests that something about our cosmic timeline is not right. The Hubble tension is one symptom. The early galaxies are another. The aging stars are a third. They all point toward a picture of cosmic history that is weirder than we have been drawing. And the future of that history, if the expansion really is faster than we thought, could be darker than we ever imagined. For most of cosmic history, the universe's expansion was slowing down. Gravity pulled matter together, trying to recollapse the cosmos. The expansion continued, but it was losing energy. Every galaxy was being dragged on by the gravitational weight of every other galaxy. Then, about 5 or 6 billion years ago, something changed. The expansion stopped slowing. It started speeding up. A mysterious force, dark energy, had begun to dominate. Instead of gravity winning, the push from dark energy won. The universe has been accelerating ever since. This acceleration has been confirmed by the same Type 1, a supernovae used in the Hubble tension measurements. Distant explosions appear dimmer than they should in a decelerating universe. They appear exactly as bright as predicted in an accelerating one. The discovery won a Nobel Prize in 2011. Now consider what a higher Hubble constant might mean for the future. If the expansion rate is 73 today, rather than 67, the universe is accelerating a little faster than we thought. That matters, because the rate of acceleration shapes the long-term fate of everything. In the standard picture, with a constant dark energy pushing at a steady rate, the future looks cold but not catastrophic. Galaxies beyond our local group will eventually be carried so far away by expansion that their light can no longer reach us. The observable universe will shrink. Distant galaxies will slide across our cosmic horizon, one by one, until only our own local group of galaxies is left visible. Then, over unimaginable timescales, even our own galaxy will age, its stars dying, its black holes evaporating. The universe becomes dark, cold, and empty. This is called the heat death. It is grim, but it is slow. It takes trillions of years to fully unfold. Atoms survive. Space remains intact. The fabric of reality stays stitched together. But if dark energy is not a constant, if it strengthens over time, the fate becomes much worse. A dark energy that grows stronger produces an ever-accelerating expansion. The push gets faster, and faster, and faster. Space itself starts to stretch more violently than any gravitational force can withstand. This scenario is called the Big Rip. It is the nightmare ending of cosmic history. In a Big Rip future, the accelerating expansion eventually overcomes the gravity that holds galaxy clusters together. Clusters fly apart. Then galaxies themselves dissolve, their stars being torn away from each other. Then solar systems unravel. Planets are stripped from stars. Stars are stripped from each other. Finally, in the last moments, atoms themselves are pulled apart. The expansion becomes infinite in a finite time. Everything is torn to nothing. How close are we to such a fate? If dark energy is a constant, as the standard model assumes, the Big Rip cannot happen. We are safe. But if the DESI survey hints are correct, and dark energy is slowly changing, a Big Rip scenario cannot be ruled out. The hints are preliminary, but they open the door. The Hubble tension, in its most dramatic interpretation, points toward an expansion rate that is faster and possibly more aggressive than we realized. It does not necessarily mean a Big Rip is coming, but it suggests we understand the force driving our universe apart less well than we thought. Whether the ending is a slow, cold fade or a violent tearing, the story of our cosmos is being written by that mysterious expansion, and the stakes extend to every galaxy in every corner of reality. Galaxies are not lonely islands. They travel through the cosmos in groups, clusters, and vast superclusters, bound together by gravity. Our Milky Way belongs to a small gathering called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and a few dozen smaller companions. Beyond our Local Group lies the Virgo Cluster, a denser collection of thousands of galaxies. Beyond Virgo stretches the Laniakea Supercluster, containing hundreds of thousands of galaxies in a tangled web. These structures exist because gravity won locally. In the eternal tug-of-war between gravity pulling matter together and dark energy pushing it apart, gravity dominated on small enough scales. Galaxies bound to each other stayed bound. They will continue to orbit each other, collide, merge, and evolve over billions of years, regardless of what the expansion does to the rest of the universe. But beyond these bound structures, everything is being carried away. The Hubble tension matters for the fate of everything that is not locally bound. The precise expansion rate determines how quickly distant galaxies recede. It determines how fast our cosmic horizon shrinks. It determines how many galaxies we will be able to observe a billion years from now, or a trillion. At 67, the expansion is slower. Distant galaxies recede more gradually. Our observable universe fades over longer timescales. At 73, the expansion is faster. The cosmic horizon retreats more rapidly. Galaxies we currently see will fade from view sooner. Our sky becomes lonelier quicker. In 10 billion years, assuming standard dark energy behavior, most galaxies outside our local group will have receded so far that their light will be redshifted into undetectable wavelengths. The universe will look empty from the perspective of any future astronomers in the Milky Way. They will see only our own galaxy, Andromeda having merged with it by then, and the handful of dwarfs that were bound to us. Everything else will have vanished beyond the horizon. If the Hubble constant is higher, this isolation happens faster. Future astronomers might look out into a sky where the distant universe has already retreated. They might have no way of knowing that once there were billions of other galaxies scattered across space. The evidence of the larger cosmos will have been erased by expansion. If the Hubble constant is lower, the deadline is slightly further off, but the ending is the same. Cosmic isolation is the fate of every unbound structure. The tension also affects the long-term evolution within bound systems. The balance between gravity and expansion determines how much room galaxies have to evolve before the rest of the universe becomes irrelevant to them. It affects how quickly gas flows into galaxies from the surrounding cosmic web. It affects how structures form on the largest scales. In a deeper sense, the Hubble tension is a reminder that the fate of galaxies is not separate from the fate of the universe. Every galaxy is embedded in the expanding fabric of space. Every galaxy feels the pull of dark energy. Every galaxy is on a journey toward a cosmic horizon that is either creeping closer or rushing in, depending on which measurement is correct. For us, on Earth, these fates are unimaginably distant. The earliest effects of cosmic expansion on our visible sky will not appear for hundreds of millions of years. The full isolation of the Milky Way will take tens of billions. But the universe operates on its own timescale, and the Hubble constant, whatever its true value, is writing the schedule. A new survey is about to sharpen that schedule even further. In April of 2024, a collaboration of more than 900 scientists released a set of results that stunned cosmology. The project was DESI, the Dark Energy Spectroscopic Instrument, operating from a mountaintop observatory in Arizona. Its goal was simple to state and extraordinarily hard to achieve. Measure the three-dimensional positions of millions of galaxies and quasars across billions of light-years of cosmic history. DESI uses a single telescope equipped with 5,000 tiny robotic fibers. Each fiber can aim at a different galaxy in the sky and capture its light. In a single night, DESI can measure the distances and motions of over 100,000 galaxies. Over its planned 5-year mission, it will catalogue nearly 50 million. This catalogue is not just a pretty map. It is a tool for probing dark energy across time. By measuring how galaxies cluster at different cosmic eras, DESI can track how the universe's expansion has changed. The faster the expansion accelerates, the more spread out galaxies should be. The slower the acceleration, the more clumped they appear. Different histories of dark energy produce different patterns. When DESI released its first major results, the patterns did not look like what the standard model predicted. The data showed a tantalizing hint that dark energy has been weakening over the last few billion years. Not strengthening, weakening. This was a shock. The standard model assumes dark energy is a constant, unchanging feature of empty space. A weakening dark energy would mean dark energy is not what we thought it was. It would be a dynamical phenomenon, something with its own evolution, its own biography. The DESI result is not a slam dunk. The statistical significance is strong but not definitive. Follow-up analyses and additional data are needed to confirm it. Cosmologists are hopeful and cautious in equal measure. If confirmed, the implications would be enormous. Weakening dark energy would mean the universe's acceleration is slowing down on the largest scales. It would mean we are not heading toward a big rip. It might even mean the universe eventually stops accelerating altogether, though recollapse seems unlikely given the current numbers. For the Hubble tension, the picture is complicated. A simple weakening of dark energy does not automatically close the gap between 67 and 73. In some models, it might even widen the gap. But the existence of dynamical dark energy opens new theoretical possibilities. It breaks the assumption that dark energy has always been the same. That assumption was baked into Planck's calculation. If it is wrong, the Planck value itself might need revision. The DESI findings have energized the field. Theorists who have long argued that dark energy must be more interesting than a boring constant now have fresh evidence to support their case. New models are being developed weekly. New experiments are being planned to test them, and DESI is still collecting data. Each year, its catalogue grows. The statistical power of its measurements sharpens. If dark energy really is evolving, future DESI results will nail down the details. If the current hints are just statistical flukes, they will fade as more data comes in. Either way, the ground is shifting. The simple picture of dark energy as an eternal constant is being challenged by the universe itself. And DESI is only the beginning of a new generation of experiments that will probe cosmology in ways previously impossible. Another major mission has joined the hunt, with its eyes already trained on the deep sky. In July of 2023, a European space telescope lifted off from Cape Canaveral and began a long journey to a stable point in space about 1 million miles from Earth. Its name was Euclid, after the ancient Greek mathematician who laid the foundations of geometry. The mission had a single grand goal: map the geometry of the universe itself in unprecedented detail to uncover the secrets of dark matter and dark energy. Euclid is a different kind of telescope from the James Webb. Webb is built for focused, deep observations of particular targets. Euclid is built for surveys. It stares at huge swaths of sky and captures them in exquisite detail, cataloguing billions of galaxies over the course of its mission. It measures their shapes, their colors, their positions, and their distances. Why does this matter for the Hubble tension? Because the way galaxies cluster and the way light bends around them tell a story about cosmic expansion. If dark energy is a simple constant, galaxies should cluster in a certain predictable pattern. If dark energy is more complex, the pattern will differ. If gravity itself needs modification, the differences will appear in the way light from distant galaxies is distorted by the mass in front of it. Euclid is designed to detect these effects with extraordinary precision. It will measure the shapes of more than 1 billion galaxies and the distances to tens of millions more. From this data, scientists can extract the most detailed map of dark matter and dark energy ever produced. They can test whether dark energy is constant or evolving. They can test whether gravity follows Einstein's equations or needs modification. They can sharpen the measurement of the Hubble constant from yet another angle. Early data from Euclid has already begun to trickle in. The first public images showed stunning views of galaxy clusters, nebulae, and distant galaxies. The real scientific output will take years to emerge, as the massive survey builds up a statistical picture of the universe. Alongside Euclid, another major survey is about to come online: the Vera Rubin Observatory in Chile. has a telescope named for the astronomer who first found strong evidence of dark matter in galaxies. When it begins full operations, it will survey the entire southern sky every few nights, building up a time-lapse movie of the cosmos. It will discover millions of new supernovae, including many Type 1, a supernovae that will feed directly into Hubble constant measurements. It will map billions of galaxies and track their motions. Together, Euclid and Rubin will generate more cosmological data in the next decade than in all of prior human history combined. The precision of Hubble constant measurements will improve dramatically. The tests of dark energy, dark matter, and gravity will tighten. If the tension is caused by new physics, these surveys have a good chance of revealing what that physics is. NASA has its own plans. A mission called the Nancy Grace Roman Space Telescope is scheduled to launch later this decade. Roman will do wide-field infrared surveys, complementing Euclid and Rubin. Another mission, the SKA, the Square Kilometre Array, will be the largest radio telescope ever built, capable of mapping hydrogen gas across the history of the universe. Every one of these projects carries the Hubble tension on its shoulders. Each will either confirm that the gap is real and new physics is required, or find hidden errors that bring the two numbers back into agreement. The coming years promise answers, and yet, even with all these tools, there is no guarantee the mystery will be solved. Science has open problems. Some get solved quickly, some take decades, some take centuries, and a few remain mysteries so deep that they shape the course of the field for generations without ever being fully resolved. What if the Hubble tension becomes one of those eternal mysteries? Imagine a future where all the new telescopes have collected all their data. Euclid finishes its survey. Rubin produces its time-lapse of the sky. DESI completes its catalogue. Webb refines its measurements. Gravitational wave detectors improve their precision. And yet, after all of this, the two numbers still do not agree. 73 and 67 remain locked in their standoff. No new physics explains the gap cleanly. No hidden systematic is ever found. This scenario is not impossible. Nature does not owe us answers. Some questions in physics have remained partially unresolved for a very long time. The nature of dark matter has been debated for 90 years without resolution. The true behavior of quantum gravity, where quantum mechanics meets general relativity, has eluded physicists for a century. A permanent Hubble tension would reshape cosmology. Textbooks would have to acknowledge that the expansion rate cannot be cleanly measured. Every paper on cosmic evolution would have to address the ambiguity. Researchers would learn to work with two possible Hubble constants, carrying both along through every calculation, letting readers decide which version they trust. The field would fragment. Some cosmologists would commit fully to the early universe value, trusting Planck and its derivatives as the true measure of cosmic evolution. Others would commit to the local value, trusting the direct measurements of nearby galaxies. A third camp would insist both are correct and that a deeper theory is needed. Research programs would split along these lines. Funding would flow in strange ways. Agencies would support both early and late universe projects, waiting for one to finally pull ahead. Years might pass without any clear winner. Cosmology has been in similar situations before. For decades, the age of the universe was uncertain by a factor of 2. Galaxy formation was a muddy puzzle with competing theories. Each of these gradually cleared up as data improved. But some mysteries linger longer than others. There is no guarantee the Hubble tension belongs to the short resolution category. Even if it is never solved, the tension has already changed the field. It has motivated more precise measurements than ever before. It has driven the development of new theoretical frameworks. It has inspired new telescopes and surveys. Every scientific generation that inherits the problem will build new tools to attack it. The tension will drive innovation, even if it refuses to yield. There is also a possibility that the tension will simply dissolve, that someone will notice a subtle, unappreciated effect in one of the measurements that nobody has thought of, that a revised calibration of Cepheid stars or a refinement in the cosmic microwave background analysis will quietly close the gap. Many problems in the history of science have been resolved this way. not with dramatic revolutions, but with careful accounting, or the tension may grow. More data may deepen the gap, push it further into the territory of real physics rather than measurement noise. Each year that passes without resolution strengthens the case that something genuinely new is happening. By the end of this decade, the verdict may be clearer, even if not fully settled. Whatever the outcome, cosmology has already been changed by the question, and in many ways, the universe has already spoken. Step back one more time. Look at the full picture. Two measurements of the same thing, made with different tools, different methods, different scientists, in different eras. Both pushed to extreme precision, both confirmed independently by multiple follow-up experiments, both refusing to agree. This is not a technical hiccup. This is not a measurement error that will quietly go away. This is the universe, in its slow cosmic voice, speaking a word we do not yet understand. The Hubble tension has come to feel like a message, a signal from the cosmos that our understanding is incomplete. Scientists have been wrestling with that message for more than a decade, and every attempt to silence it has failed. The message only grows louder. What is the universe trying to tell us? Maybe it is telling us that dark energy is not what we think, that the 70% of the cosmos we cannot see is more dynamic, more complex, more alive than our simple models imagine, that the void between galaxies is a field of activity we have not mapped. Maybe it is telling us that gravity itself needs a correction on the largest scales, that Einstein's beautiful equations work within galaxies and solar systems, but start to fray when stretched across the full cosmos, that the fabric of space has properties we have not yet recognized. Maybe it is telling us that new particles exist, sterile neutrinos, axions, or something stranger still, ingredients in the cosmic soup that we have missed, because our detectors are not sensitive enough or our theories have not pointed us in the right direction. Maybe it is telling us that our entire cosmological model is a good approximation that is starting to show its cracks, that we stand at the beginning of a scientific revolution comparable to the one that brought us relativity or quantum mechanics, a revolution that will replace the familiar picture with something stranger and more true. Or maybe it is telling us something none of us have yet imagined, something that does not fit into any of our current boxes, a truth about reality that will require new mathematics, new concepts, new ways of thinking before it can even be expressed. Whatever the answer, it will come from patient work, from more data, from sharper instruments, from theorists willing to explore the wildest possibilities, from observers willing to verify those possibilities against the sky. Science moves forward, not by guessing right, but by testing everything. The Hubble tension is one of the most exciting problems in modern physics for exactly this reason. It is a crack in a wall that we thought was solid. Through that crack, something is shining. We do not yet know what, but we can see its glow, and we cannot look away. In the meantime, the universe continues expanding. Galaxies drift apart, carried by space itself on a journey neither they nor we can alter. Whether the expansion rate is 67 or 73 or something in between, the cosmos marches on. It does not care about our confusion. It simply continues being what it is. Our job is to keep watching, to keep measuring, to keep asking, to refuse to accept an answer just because it is convenient. The universe has kept its secrets for billions of years. It can keep them a little longer, but we are patient too. And every generation of scientists passes the tension to the next, armed with better tools and sharper questions. Someday, someone will crack it. Someday, the two numbers will become one. And on that day, the universe we thought we knew will be replaced by a deeper, stranger cosmos. Until then, we listen, and the message from the stars grows louder with every passing year.